Okay, so for our last lesson of Unit 3, we're looking at more optimization problems, part 2. So just to get you some more practice with that. And we have 2 examples that we'll do today before you try some homework from the worksheet. So let's look at the first one here. This up. So Steve is building a rectangular wooden toy chest so that the length is 2 times its width. So again, if you have a highlighter or a different color, and for these questions, it might be good to just point out what you think the important information is. So the length is going to be 2 times its width. So we'll write that out when we do the diagram. He has picked pine for the top of the box, the front of the box, and the 2 sides of the chest. So just keep that in mind. So again, I have pine for the top, front, and 2 sides. So 4 of the sides. He will use fiberboard, so whether you want to change the color of that or not, he will use fiberboard for the back and the bottom. Okay, so there's 2 different types of wood. The chest has to have a volume of 0.3 meters cubed. So it's kind of helping us with what the size would be given that the inside volume to fit with toys, right? It's a toy chest. Yep, is going to be 0.3 meters cubed. Volume is cubed. Pine costs twice as much as fiberboard, which is the whole point here. He wants the part, if you see here, right, that you can see, right? You can see the top, you can see the front, you can see the 2 sides to be the more expensive wood. And then it's probably going to be up against a wall. So the bottom and the back you won't see can be cheaper. That's just really being smart, which is trying to save his money, right? Find the dimensions. So here's really the question. Find the dimensions that will minimize the cost of the chest. So obviously when we're talking about cost and value, right, and we're not talking about revenue, we're talking about money out of your pocket, we want to minimize that cost. So this would be our first equation. We want to minimize cost. We want a cost equation. So I'll just kind of write that out for you so you can have this to refer to. So we need a cost equation, and then obviously when we differentiate, and then we're going to use the second derivative to confirm and to prove that it is a minimum. So first thing we can do, right, if it's talking about this toy chest, we can see that it's 3D, it has volume. I'm going to do my best to draw a 3D shape here. Again, the same as I would expect from you, not perfect, but so that you can make out what it is good enough. Let's see here, go like that, go like that to make it 3D. Go across, again, just, I'm hoping actually, and what usually is the case is yours does look better than mine. I was going to change the color, but you know what? I'm going to change the colors when I'm going over the front and the top and the, so I'm going to leave the actual drawing, 3D drawing, to be just all one color. I think that's good enough. And again, if you did it that, I would be happy with that. So now let's label, let's start from the beginning here. Okay, so here we have the length, right, is 2 times the width. So we have to be careful because it's 3D. 3D means I have 3 different dimensions. So I don't just have length and width, but I also have height. So let's label, let's take a look at which ones are the width, let's say, right? So the width would be, let's do these as single ticks. 1, 2, that's a width. 3, 4, I think that's it then, right? Just the 4. 2, 1, 2, 1, 2, 1, 2. And we label the width as, again, you can put W. I'm going to label it as X. You can label it, again, as whatever variable you want. You can have your first initial of your first name, your last name as the length. It doesn't matter. And then the length is going this way, right? Just like the 2-dimensional shapes that we did before with the garden and stuff. So we've got length here, length here, length here, and length here, just to go over. And you could change the colors of these two if you wanted to. And if the length is 2 times the width, then we just do 2 times what represents the width. So now we need our let statements, right? But let me just do the height first as well before we do our let statements. And so then the height would be, if you can see here, this would be the height, right? So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So I would have 4 heights. And again, you can label that y, if you wanted to, I'm just going to leave it as h as height. But again, it would make perfect sense to label it as y as well. So let's do our let statement. So it says the dimensions that minimize the cost. Like we said, we need a cost equation. So we have to let probably C, right, represent the cost. And then in what type of unit. It's probably unlikely that it would be in change and cents instead of dollars, but you never know the question, so you have to state. Let C represent the cost when we do our cost equation, and that's going to be, like I said, in dollars this time. What was X? Let X, I'm just going to say here, represent the width, and be careful that it is the width. You don't want to get that wrong. And what units am I talking about here? If I've got meters cubed for volume, then the width is just one dimensional. It would just be in meters. Let 2x, you don't have to necessarily put that statement because you already have what x is, right? But again, if you want to, it's just being more clear, and it's just going to help you with your therefore statement at the end when you do your conclusions, because you're going to make sure you answer all of these. So let 2x represent the length, which would be in meters. And we have, I had h, I don't know if you have y, let h represent the height. And those are, so we have our 3 dimensions, length, width, and height, and then we have our cost equation. And for now, that's all I know that we need to have, right? So let's go ahead and figure out what our cost equation is going to be. So we have to be careful here. We know we have 2 different types of costs, because we know that pine costs twice as much as fiberboard. I know that I have the cost of buying the pine, and I know I have the cost of buying the fiberboard, right? So let's work out the pine for right now first, just because it came first in line. It didn't matter. You could have done the fiberboard first. So I'm calculating, and this is where I'm going to do different colors here. Let's go orange, because I don't have that up there anywhere. Actually, no, it makes more sense to do pink, right? And have it match what I underlined. So pine is going to be at the top. So the top is this. Again, I wouldn't, even though it's area, right? The whole entire thing, I wouldn't color it in. And you'll see why when I'm done, because then you won't be able to differentiate between that and the other 2 fiberboard ones, because just trust me, everything will be colored in with pink if you were to do that. So the pine is going to be for the top. It's going to be for the front, which is this part here. And it's going to be for the 2 sides that you can see, right? So you can see this side, and you can see this side here that we just have inside like this. So we have, I know it's hard to imagine, we've got the top, the front, the right side, and the left side, let's say, right? So let's do the, I'm going to go over here. So the top, again, we're talking about area. So length times width. So the width is x and the length is 2x. So x times 2x. I'm just doing over to the side. So the top is going to represent 2x squared, right? Now let's do the front, the next thing that was stated in the question. So the front is, again, it looks like we've got height here times length. So 2x times height, which is, again, just 2xh. That's all I can do there, right? Then we've got the sides. So the right and left side here is the width and the height. And again, this would be, again, 1 tick, the width, times 3 ticks, the height. So I'm just going to get one of them and multiply it by 2. So the sides, I'm going to put, doing both sides at once, is going to be x times h. Does that make sense? The width times the height, right? Or like length times width of that rectangle side, and then times 2 of them. So that's going to be 2xh. Okay, and so then that would be my amount of the pine. I don't have any prices or anything. It's just going to be, my cost equation is, the top is going to be 2x squared once I figure out what x is. So 2x squared is the top, plus the sides, or the front we could do next. Let's say 2xh plus the sides is also 2xh. I'm just double checking here. 2x squared plus 2xh plus 2xh. So we don't really need to differentiate which is which, but that would be our equation for the amount of pine. And then to that, we're going to add, let's change our color, the fiberboard. So yeah, I don't have orange. So the fiberboard is going to be used for the back. So again, kind of work with me here. The back would be this part is orange and this part and this part and that part, right? And also the bottom. So again, this part, this part, this part, and this part. Hopefully you can see those two there. So again, you might want to go, I can go over to this side, I can go down below. I'll just keep it all on one side here. So let's say the back, to figure out the area of the back, would be height times length. So the length is, again, 2x times h. So 2xh, you could have just gone right to 2xh, right? And the bottom, the area of the bottom that we're buying would be, again, length times width there, x times 2x. So we already know x times 2x. I can go right to 2x squared, let's say. And so then that part of the equation would be, I'm just going to keep my squared first, just to kind of, usually you've got the higher exponent first, right? Plus 2xh. But you could have done it the opposite, 2xh plus 2x squared. To me, you know, probably now by grade 12, that just looks weird to you, maybe being out of order, but again, it doesn't matter. And this is the fiberboard. All right, that's the fiberboard. And what am I missing here that you might hopefully have noticed by now? I've got the pun and I've got the fiberboard, right? So I've got all the pink here done and I've got the blue part here done. Sorry, I technically should have done that in blue. But here, pine costs twice as much as fiberboard. I haven't accounted for that. This is my cost equation, right? So I do need to take into account that the pine is twice as much. So what I'm just going to do is put a 2 out in front here, because whatever I'm purchasing of pine, if I just multiply it by 2, that would be stating that it's twice as much as what the fiberboard is. And then let's just simplify this equation. Basically, this is it for the equation. We're just going to try to make it look a little bit better, right? So I can do distributive property there, and then just collect like terms if I have any. So that would be 4x squared plus 4xh plus 4xh. I could put those together, but I'll just write it separately for now. And then this is just plus 2x squared plus 2xh, right? So again, if you want to color code your like terms, that's up to you. So I've got 4x squared and 2x squared, and then the others, the xh, xh, and xh, which is nice because that means it's going to condense down to just 2 terms. So the 4 plus the 2 is 6. Again, it's still x squared when you're collecting like terms. And then I have 4 plus 4 is 8, plus 2 is 10xh. Again, it stays xh. So that's my cost equation. If I want to put a box around it or whatever, my cost equation is 6x squared plus 10xh. And what do you notice that we've done from the previous videos of optimization problems? I have, I'm just gonna put that in red, 2 variables still, right? X and h, width and height. Which means when I have 2 variables, I need another equation to substitute, right? Have 2 variables, need another, I'm just trying to fit it in here, equation. So I think it would be too squished, unless if it's okay if you have this down, I'm just gonna erase that just so I don't have to erase everything. And I'm just gonna do the second equation off to the side and then we'll move the page down. So, okay, I'll leave it in red. So the second, so this is like our equation number 1, right? Our equation number 2 here. Again, just go back to the question, what else does it talk about? The only other formula I could use here is it talks about the volume. So again, you'll be given the equations, but what's the volume of a 3D rectangle? Length times width times height. You hopefully just know by now, right? And what numbers can I plug in there? I don't have a value for length or for width or for height. I just know that the volume though is equal to 0.3 meters cubed. So under V, I can put 0.3. What's taking place of length? 2x. So I'm going to change my L to 2x, right? To be similar to my first equation. The width is x and my height is height. So I have 0.3 equals 2x times x, 2x squared h. Are we good with that? And then I need to rearrange or isolate for one of these variables. I can isolate for x, but if I do, then I have to take the square root of it. So maybe I just isolate for h, might be easier. So if I isolate for h, to get h by itself, I would simply just divide by 2x squared on both sides, right? So just writing that out here, divide by 2x squared, and I'm just not going to do it on this side because 2x squared divided by 2x squared would be gone. And again, if you did that for me as well, that would be fine, leaving that step out. And then I just went ahead and I said, okay, what is 0.3 divided by 2? Because can I turn that into, is that any better for me not to have a number on both the numerator and the denominator? And that turned out to be 0.15. So that's on top, but I still have the x squared on the denominator. So I still have to leave it like that. And so then we're gonna sub this, and this is where I have to clear my screen, sub into equation 1. So I'm gonna write out this equation once I clear my screen and then sub this equation into it. Okay, so we can rewrite that though. So I have here my equation 1. Sorry, again, is the cost equation was 6x squared simplified plus 10xh, not too bad. And then my equation 2 was the height is equal to 0.15 over x squared. So just simply sub in h equals that to get my cost equation with just one variable. So I have 6x squared, I don't do anything, plus 10x, I don't do anything. And when I see h, I know it's a fraction, so I put a bigger bracket there and I put 0.15 divided by x squared. So what's happening between these terms is just multiplying across the top, right, and multiplying across the bottom. So that's going to equal 6x squared plus, if you go ahead and do, you know, there's an x there, but 10 times 0.15, 0.15 is equal to 1.5. But then what I did was if there's an x as the numerator and an x in the denominator, one of them I crossed out. So then I'm just left with over a single x. Okay, so then my restriction again would be that x cannot equal 0 because I can't divide by 0. But also we talked about in the previous videos just restrictions of what makes sense in the problem. Well, x is going to represent my width, right? I can't have 0 width and it can't be negative. So we already know from my restrictions that x is going to have to be greater than 0 anyways. And that's what we will also prove when we do our first and second derivatives here. So that's as far as I can go, but that's my now cost equation, so C. So now let's differentiate. So just over here, let's take the derivative, differentiate, do C prime. So to differentiate here, what might be easier, like we've said previously. So I've got my 6x squared. Actually, I'm just going to write it out, sorry, not as C prime yet, just as C, because I want to rearrange this. So I have my 6x squared plus my 1.5, but if I bring that x up to the top and make it x to the power of -1, that's just, for me, that's easier to differentiate than using it as a fraction, right? So now when I get my derivative, I would have the 2 in front is going to be 12x to the power of 1, right? And then the -1 comes in front and multiplies. So it's going to be -1.5 now x. And now be careful because it's subtract 1. So -1 subtract another 1 is -2. Don't make that a 0 and don't think it goes away. Okay, so then just to rewrite that to make it look a little nicer, and to set it to 0, right? The whole purpose is to differentiate, set it to 0 so I can get my critical numbers. My x value is equal to then 12x minus the 1.5, but I might want to bring that x to the, we don't like negative exponents, down to the denominator and have it be x squared to solve for my 0. But let me just see here on the other side. Yeah. How do I start solving for x here, right? Factoring is not really an option right at this moment. You might be thinking, okay, how do I do that? So what if we just tried to clean this up? So let's get a common denominator, right? And make this into maybe one term. So if I want a common, I should just put CD, but common denom I'll put. Between here, the common denominator would be x squared, right? So just to change my color, if I'm going to have an x squared down here, or multiply by x squared and then multiply the top by x squared, then I would end up with x squared on the bottom, right? This is already x squared, so the minus 1.5 doesn't change because that's already what I want it to be. But the top would be 12x times x squared. So that would still be 12, but then x times x squared would end up being x cubed, and setting that equal to 0. So I have 12x cubed minus 1.5 over x squared. And again, when you set things equal to 0, if you remember here, over 1, when you cross multiply the 0 times the denominator, you end up, and then it's just going to be 0. So you end up with just 0 equals the numerator. I don't know if you can see that color in the video from afar. So I'm just going to erase this to have some more room. And I'm just going to move this over here. Whoop, okay, so then I end up with 0 equaling the numerator. So is this helping me at all to solve for x? 0 equals 12x cubed minus 1.5. Let's see what happens again if I was to common factor, because that's to solve for x, I need to factor in some way. I don't know how to factor this yet. 12 is not a cubic number, right? Like a perfect, not perfect square, but a number, because I've got cubed here is why I'm trying to cube it. I can't think of a number times itself 3 times. That would be 12. So what if I pulled out the 1.5, right? That's kind of what else can I do here? So 12 divided by 1.5 would leave me with 8x cubed, and then I would just have minus 1. Now, hopefully this is kind of ding, ding, ding going off in your head that 8 is a cubic number and 1 is a cubic number, right? If I were to take the cubed root, right, of 8x cubed, the cubed root of 8 is 2, 2 times 2 times 2, and then x. And the cubed root of 1, 1 times 1 times 1 is just 1. So that might be getting me somewhere. So this is a difference of cubes. I'm not going to write that down. You might want to write that down, though. That's a difference of cubes. I will, off to the side, just remind you how to do a difference of cubes. So yeah, I'll write out here, difference of cubes. If I have a cubed, and this is a minus 1, so it's different for adding, right? Minus b cubed. The answer is here a minus b as a binomial. And then you have a trinomial, that's a squared plus ab plus b squared. So your only minus is in front. And then you have a, and if you remember, it's an unfactorable trinomial that you will end up getting. So then, well, let's get there first and then I'll explain that further. So you're just going to copy down the 1.5, right? So then I have, again, a minus b. So here's a and here's b. So 2x minus 1 is my binomial. Then I have a trinomial, a squared. So 2x squared is 4x squared plus a times b, which is just 2x, plus b squared, 1 squared is 1. And we already know, but if you wanted to think that through, again, you can write down, I just don't want to write down for room here, that this is an unfactorable trinomial. So there's no solution to that. If I were to set 4x squared plus 2x plus 1 equal to 0 and solve for x, there is nothing, right, that multiplies to 4 and adds to 2. That's not going to work because it's all adding there. But I can set this binomial, 2x minus 1 equal to 0. So then, again, here 2x would equal 0 plus 1, divide by 2, divide by 2. X is going to equal 1/2 or 0.5, however you want to write that down. So there we go. Finally, we figured out what our critical number is, just to put that in red. And then again, I have to clear my screen. So therefore, my critical number is at x equal to 1/2. And again, because, just to put that in there, at x equal 1/2. And I don't have this side because it's unfactorable. I just narrowed it down to just one critical number. So now to confirm, I want to do the second derivative test, right? Not the chart, but just figure out the second derivative, subbing in the x value of 1/2 to confirm what? To confirm a minimum. So we want to smile here, right? So we want that to be the answer to be greater than 0. So let's see. So let's just clear this. So I've got an x value, or just to write out here, critical number at x equals 1/2. I can write down what my first derivative was over here from before. So my first derivative was, again, we like the exponent to be in the numerator, even if it's negative. So the 12x minus the 1.5x to the power of -2 is what I will use to get the second derivative. So then on x, that would just be 12, x to the power of 0, which would be gone. -2, be careful, times -1/2 is actually a positive 3, x minus another 1 to the power of -3. So I have 12 plus x to the power of -3, which again, when I'm plugging in values now, I know we don't want the negative exponent, so you might want to write that out as 12 plus 3 over x cubed. And now you're going to sub in the value of x equals 1/2, which might be easier using the decimal. So I have to write that out. The second derivative, plugging in a value of 1/2 for x, right, is equal to 12 plus 3 over 1/2 cubed, and whether you have that in brackets in case it was negative. And here I have 12 plus, so if I do the, depending on how your calculator works, right, be careful. You might have to take 0.5 cubed to get that number and then do 3 divided by that number, or does your calculator do 3 divided by, and you might have to use brackets here, right, to cube it. You're gonna have to, hopefully you know your calculator by now. You should end up with an answer of 24 just for that whole fractional portion. So then you have a final answer of 36. So again, 36 is greater than 0. So if 36 is greater than 0, then I just want to keep it down here, then I am concave up and I'm smiling. And if I'm smiling, then that produces a local min, right? So here I would have a local minimum at x equals 1/2. So that confirms minimum, right? That's what I wanted. So now I can just get my conclusions and get what my my let statements, get what my width. It just asks for the dimensions. So the width, the length, and the height it would need, right? So in conclusion, I'll just do that in blue here. The dimensions are, depends on what it asks, right? All it's asking for is the dimensions. So in conclusion, the dimensions are the width represents x, and x was 1/2. So we already had the units up in our let statement. The units were meters, and also here meters. So the width is 0.5 meters. The length, right, was 2 times x. So 2 times 1/2 is equal to 1 meter long. And my height, and this is going to be the dimensions that minimize my cost. If I wanted to go bigger or smaller than this, that's fine, but just I would know that it's going to cost me more money. My height equation, if you remember, was 0.15, just go back and look at it, over x squared. When we isolated for h in that second equation, that's what we got. So that's what we can use, right? We need it with just x. So we can plug in the value of 0.5. So 0.15 divided by 0.5 squared. Again, be careful with your calculator there, whether you have to put brackets around that or not. You should have an answer of 0.6 meters. So there we go. Those are the dimensions that will minimize the cost of this 3D box for whatever, toy chest, coffee table, width of 0.5 meters, a length of 1 meter, and a height of 0.6 meters.